Hello, hello. Can somebody just let me know if you can hear me? Okay. So this is the, oops. Just a sec. Okay, sorry about that. Okay, okay. So this is the AMACSS review seminar for the MATA37 midterm. So a little bit about AMACSS. We are the club that sort of does these review seminars for the majority of CMS courses, particularly for you guys in the first year and for most courses in the second year as well, and a variety of different ones in upper years as well. So we're going to get started. My name is Omar. I'm going to start with the first set of questions, and the set of questions is about uh, Riemann integrals and in general just integral properties. So it's these three questions here. The first being a Riemann integral proof, the second being a indefinite integral proof, and the third being a Riemann computation. Okay, so get started now. Okay, so I think I have an outdated version of the slide, so this is a bit errored. We have an AB there and an AB there. Okay, so just to make sure everybody can still hear me, right? Is my
Yeah, you're
okay.
Yeah.
Okay, good. Okay, so this is our first question. So we have let A, B be in the reals with A less than B. We have f and g being integrable functions such that f of x is bigger than or equal to g of x, which are both bigger than 0 on the closed interval AB. We want to prove that this integral on the left is less than or equal to the integral on the right. An obvious thing here is that we can't just use properties of definite integrals. We sort of have to use the Riemann definition here. So yeah, so let's get into that. So at the start of any Riemann sort of question, we need to define a partition. So we're going to start by doing exactly that. So we're going to let the set of xi's from I equals 1 to n be a Riemann partition of our closed interval AB. Okay, and what we want to show is exactly that thing there, right? So this is our want to show. Okay, so we're going to leverage the fact that we have our supposition here, which is this inequality right there. So whenever you do these Riemann sort of questions, you need to make statements about all i's, so from I equals 1 all the way through n, and then afterwards we'll link them together to sort of form them into a sum. So we're going to start with for all I equals 1, 2, all the way to n. We know, well, and we also know that in Riemann, in anything to do with Riemanns, we use xi star. So first we're going to define our xi star. We're going to let xi star be in the interval xi minus 1, xi. And we're going to let it be arbitrary. The reason why we take it to be arbitrary is because we know that this should work for any xi star in there. So we're going to prove that it works for all of them. Okay, now that we did that, we're going to, continuing with the fact that for all i's, we know that f of xi star is bigger than or equal to g of xi star is bigger than 0. And that's just directly from the hypotheses. Okay. Right, and this is just because xi star is in xi minus 1 to xi. And we know that this is a subset of AB, right? So because we know that this inequality holds for over AB, we're now working with a smaller chunk of AB, so we know that it'll hold here as well. Okay, now that we came here, we can continue. So we know that we're not working with f of x and g of x, we're working with these functions up here. So we're gonna try to get those to appear here. So if we wanna get from what we have here to sort of these two functions here, what would be the first step we take in sort of manipulating this? Would we do a reciprocal, or would we like add the 5 or something else? Okay, reciprocal first, yeah. So we're gonna now take our reciprocal. So this implies, so one thing that's important is using proper connectives. So we're gonna use an implication symbol here. We know that if this above thing is true, then it must be the case that 0 is less than 1 over f of xi star less than or equal to 1 over g of xi star. Okay, pretty straightforward. Exactly. We know the reciprocal exists because they're both non-zero. That's in the supposition. Cool. So now that we have this, we can then add the 5 because we know that's what's missing from what we have. So now we can add 5 everywhere. So this then implies, here we can use, we could use an if and only if, but then implies works just as well. So we can do 0 is less than 1 over f of xi star plus 5 less than or equal to 1 over g of xi star plus 5. Okay, nice. So now that we have this, so we now have sort of the functions that we want. So you can think of this as the function that we're working with. So most of these proofs just work with a simple like f or g. Here we kind of created our own functions, but the general proof here is going to be the same thing. So now what we're going to do is if we want to make the Riemann definition of a definite integral appear, we know we need a delta x and we need a sum. You can technically go either way here, but I'd like to start with multiplying everything by delta x. So this is if and only if, and again, you could use an implication here, but an if and only if works kind of better. So we're just going to multiply a delta x here everywhere. So 0 times delta x will remain 0 times, so 1 over f of xi star plus 5 times delta x less than or equal to 1 over g of xi star plus 5 times delta x. So, okay. So how do we know that the inequality here stays in the same sort of direction? Exactly, delta x is positive. So these are the sort of things you need to justify, right? So here we're going to say that as delta x is equal to b minus a over n, and we know that a is less than b. So that numerator is positive and n is the number of items in our partition. Of course, that's positive as well. So positive and positive together, that makes it positive. Cool. So now we have this. And now whenever you have a sort of inequality like this, you can now apply a sum to everything. Because basically the idea is if you have a bunch of larger things and a bunch of smaller things, adding the larger things will yield a bigger sum than if you were to add the smaller things. So we're now going to say this implies that the sum from I equals 1 to n of 1 over f of xi star plus 5 times delta x is less than or equal to the sum from I equals 1 to n of 1 over g of xi star plus 5 times delta x. And notice that we kind of dropped the 0 at the tail of this inequality. There's not a particular, only reason we're doing that is because it's kind of irrelevant now. The only reason we needed a 0 was for some of the previous steps, so we don't really need it anymore. So yeah, and now again, to sort of justify this, I just say as the above held for all I. And that's sort of just reinforcing the idea of like, if we have a bunch of bigger things and we add them, it'll be bigger than the sum of the bunch of smaller things. Okay, and the next step we can use here is limits. So we can now, the only thing missing here from like the Riemann definition is limits, right? So we can now apply limits to both sides. So we're going to have that the limit as n approaches infinity of the sum from I equals 1 to n of 1 over f of xi star plus 5 times delta x is less than or equal to the limit as n approaches infinity of the sum from I equals 1 to n of 1 over g of xi star plus 5 times delta x. And there's a key sort of thing you need to say here to justify this. We say this is by the monotonicity of limits. So this is like the exact words of Kathleen if you were to look at her solutions for some sort of problems. So it's by the monotonicity of limits. Cool. Okay, now that we have this, we can now just sub in our Riemann definition of the definite integral, right? Exactly, Divi. So we can now, now we're going to use an if and only if. If and only if just says that it's kind of like used here because they're exactly equal, so we can go in both directions. So, but again, you could use an implication here. Don't worry too much as long as you have connectives. If you're not sure which to use, an implication is safer than an if and only if. So now we can just use our definition here. So it's going to be the definite integral from a to b of 1 over f of xi. Well, not xi anymore. Our function is this thing. So instead of xi, we just keep it as f of x at this point. Plus 5 dx is less than or equal to that one there, which is, by definition, the definite integral from a to b of 1 over g of x plus 5 dx. And this is by Riemann definition of the definite integral. Okay, and if we notice, this is the exact thing that we wanted to show. So at this point, we are finished this question, and you would put a little black square. So this is the solution here. If anybody would like to take a screenshot of it. Any questions about this one? And just see if this would still hold if we had absolute f of x is bigger than or equal to absolute g of x. I would be interested in that too. I don't think we're quite able to do that at the moment though. So any questions about the particular one here, or are we free to move on to the next one? Okay, we'll move to question 2 then. So question 2 is a bit easier. It's a indefinite integral proof. And basically, so unlike having the I think it's like 6 or 7 definite integral properties, there's only really 2 for indefinite integrals, which is the fact that they split over like addition and also scalar multiplication, sort of like the fact that they're linear together. So yeah, so this is kind of a combination of both of them that we're going to want to show. So we want to show that the indefinite integral of f of x plus 3 g of x is equal to the indefinite integral of f of x dx plus 3 times the indefinite integral of g of x dx. Okay, so, and again, the suppositions here are that f and g are integrable on their respective domains. Okay, so we can start this. So proving an equality, right, you can either start from left-hand side, show that it equals right-hand side and show it equals left-hand side, or you can do a mix of the both. In this case, though, I'm going to start from the right-hand side. So consider the right-hand side. This is equal to the indefinite integral of f of x dx plus 3 times the indefinite integral of g of x dx. Okay, and so, okay, one thing we should have said before is let f and g, so big F and big G, be antiderivatives of little f and little g, respectively. right? And what respectively here does, it means that big F belongs to little f and big G belongs to little g. Okay, cool. Now if I move this down to make it a bit cleaner, so now we're going to start our actual work. So consider this. Now, what would this equal to in terms of like just using big F and big G? Yeah, exactly. So yeah, plus C. In this, technically by definition, they each have their own plus C. So we're gonna call them C1 and C2 here. So for the first integral, we're gonna call it big F of x. We know that this indefinite integral here has its own plus C sort of constant that can represent anything. So we're gonna call it C1. Similarly, the second one, we know that the antiderivative is g of x, big G. And again, this has its own plus C. Like think about if you were doing this by itself, right? If you were computing this by itself, it would have its own plus C. So we're going to call that C2. Okay. And now we sort of want to group these into one simple single integral definition. So what we're going to do is we're going to start by grouping our f of x plus 3g of x because we know that that's the thing we're trying to show. So if I group f of x, big F, plus 3 times big G of x together, we get this. And what's left over is plus C1 plus 3 times C2. Can you just let f and g be families of antiderivatives? Technically, but I think like it wouldn't really show as much a clear proof because we want to have like a sort of plus C at the end, right? It would work if you generalize it that way. Yeah. So now that we get to this point, it's kind of like we know that this thing is the antiderivative of, so little f plus 3 times little g. We know that it needs its own plus C though. So we look at these constants that we have here. These constants can represent anything, right? And by taking C1 and C2 to be random numbers, we can make this form any number. So technically, if we let C, just plain C, to equal to C1 plus 3 times C2, we basically get that this thing is still equal to f of x plus 3 times big G of x plus C. And again, the C works just as well as any other C because it can represent any number because the C1 and C2, we can choose them to be anything to represent any number. Okay, cool. So, and if you notice, this is the antiderivative of, this is what this left-hand side integral evaluates to. If you were interested here, you could do a sort of guess and check approach to sort of check that it works out, right? If we differentiate this, so if we differentiate here, we get little f of x plus 3 times little g of x. And we know C is constant, so it'll go to 0. And yeah. So, and again, we're done our proof at this point. So in this particular question, you technically don't need to check, but just to show that for like your own intuition. And then yeah, again, we're done the proof here because we were trying to prove an inequality, and we showed that the right-hand side equals left-hand side. That literally does what it's supposed to, right? We prove that that equals that. So at this point, we can just put our black square and we're finished the question. Okay. Any questions about this one? Okay, nice. So if we now move to question 3. So the above two are two proofs. Now we have a computation. So we have a Riemann partition defined for us for some interval a, b, where a, b are both real and a is less than b. And we want to compute this sort of Riemann sum, limit of a Riemann sum. Okay, so for computing this time, so consider the limit as n approaches infinity of the sum from I equals 1 through n of, no need for the brackets here, so I'm just going to drop the brackets since everything's multiplied. It's kind of clear anyways. 7 by n root 4 plus I over n. Okay. Any idea how we can sort of evaluate this? Integral from 4 to 5 of 7 square root x dx. That honestly is probably right. So why can't we just why so normally whenever you guys see these things, you're used to just computing limits of Riemann sums using like the prerequisite formulas. Why does that not work here? Right, so if this was like another type of function, you could have just like used the linearity of the sum and sort of split it, used what you know, and sort of use your prerequisite formulas. Uh, no, right? Because like think of like the times where not because n is approaching infinity. Yeah. So like what Max says, we only have some formulas for I squared, and I cubed, not square roots. In general, like we can't distribute this sum, right? We can't. It's not linear. We can't take it inside the root or anything, right? So we don't know how to work with that. So exactly that. So that approach here wouldn't work, and instead you should be looking at, let me turn this into an integral because that could be easier. So is that clear though? Why we're taking this approach? Okay, I assume so. If anybody has any questions, just leave them in the chat or unmute. But yeah, okay. So what we can do now is we can start by, this is sort of like those reverse engineering questions now. So we can start by sort of picking a delta x. What would be a good choice of delta x here? 1 over what? Yeah, so 1 over n. I think what you meant was like the length of 1. But yeah, so 1 over n. So we're going to choose delta x to be 1 over n. Okay. And immediately when we choose delta x, what does this tell us about something else? Does this give us any more hints about anything else? Exactly. So b minus a is equal to whatever the numerator of our delta x is. In this case, that's going to be 1. Okay, so now if we now rewrite this with our newly gained information, this is going to equal to the limit as n approaches infinity, sum from I equals 1 to n of 7 times the root 4 plus delta, oh, sorry, I delta x times delta x. Now I split up that 7 times the delta x. I brought the delta x here just so it's a bit more like kind of what we're used to looking at. So this is what we have now. So what would a next sort of action be? Take a equals 4, but why? Yeah, so it's, the reason why you'd be picking a is from the definition of xi, right? So like we know that xi for all I equals 1 through n. We know that xi is equal to a plus I delta x. So you're looking for this sort of form. We see that we have that form right inside this root. So the natural choice here would be to take your a to be 4. Technically, there's like infinitely many options you can do here because you can turn this 4 into like, for example, 3 plus 1, choose your a to be 1, and then have a function of the 3 in it. But obviously, your easiest choice would be to take the a as 4. Okay, so we're going to choose our a to be 4. So the second we choose a to be 4, what other information does that give us? B equals 5, right? Because we said that b minus a, above here, we said that b minus a is equal to 1. So if b minus a is equal to 1, if we rearrange for b, that tells us b is equal to 1 plus a, which in this case is now going to be 1 plus 4, which is 5. Cool. Okay, so now we're getting really, really close. So we now have this is equal to the limit as n approaches infinity. So now if we replace what we just found out, if we sort of apply it, we now have 7 root of xi delta x. Okay, what is sort of the next thing we can do here? The last thing we need to find. Choose f of x, right? So we're technically choosing f of x, and it would be plugging in f of xi. So you're choosing, yeah, you're in general, you're choosing the function, right? So what could you choose the function to be here? Yeah, 7 square root of x. So just one important thing is that whenever you're choosing the function, you're choosing a general f of x, right? You're not really, it's not like you're choosing f of xi, you're choosing f of x because you're just choosing the function that we're integrating. But then this thing here, because it's using xi, this is f of xi. I don't know if that's what you meant, but yeah, just a clarification, just in case anyways. Okay, so yeah, now that we have that, that's sort of, we'll clean this up entirely. So this is now going to equal to the limit as n approaches infinity, sum from I equals 1 through n of f of xi times delta x. Cool. And now that we got this, this is like exactly what a Riemann definition looks like, right? So we can now just substitute that. So we know that this is now just equal to the definite integral from a to b of f of x dx. And this is by the Riemann definition of definite integrals. I'm just going to leave it as that. So now we could just sub in what we know everything here is. So our a, we found above that our a is equal to 4, our b is equal to 5, and our f of x is equal to 7 root x. This is going to be 4 to 5 of 7 root x dx. While I know this is computable, we may as well just pull a 7 out here, because why not? Okay. What would the antiderivative here be? So the antiderivative of root x. 2. Yeah, exactly. So in general, we can write this as x to the half dx. And we know that this is just going to be 7 times. So now it's going to be x to the, we're going to add 1 to the exponent. So it's going to be 3 by 2 divided by 3 by 2. And looks bad, sorry. And this is going to be evaluated where? At 4 and 5 at our endpoints. And an important piece of justification is that at this step, you always need to say by FTOC1. So it sounds like we're nagging about like justification, but you would lose marks if you didn't justify these. So it's important to be in the habit of doing it. And then this is just equal to, so we can take the constant out, right? So this is going to be 14 by 3 times x to the 3 by 2 evaluated at 4 and 5. This is going to equal to 14 thirds 5 to the 3 halves minus 4 to the 3 halves. For this type of question, I don't think you need to compute what those numbers are. It's not too bad to compute, but I don't think you would have to. It's just like root 25 minus root 64. But I think you could just leave it like this. So for now, we will. Tony, yeah, like what the chat's saying? No, you don't. Only for FTOC2. Oh, then Garbo, I don't think the use of words really matters that much. I was more so saying the like intuition. It both ways are totally fine. There is an infinite number of elements you could pick with a difference of 1 since R is closed under subtraction simply. Yeah, exactly. There are infinitely many answers, exactly. Cool. All right, so like we said above, you could have chosen your A to be something else, right? You could have expressed this 4 here to be like 3 plus 1, chose your A to be 1, have your function have a 3 in it instead. So it doesn't really matter. Well, technically it wouldn't be a different answer. It would be the same answer though, right? Because you'd be integrating a different function over a different domain. Yeah, question 2, sure, here. Do you just want to see the solution or is there a question about it? Okay, is that enough time now? Okay, nice. Okay, so now just going back to say one last thing about this third question. So what we are evaluating here is a limit, right? So a limit doesn't have infinitely many answers. It has one answer, right? So we need, it will have one answer. So as there are infinitely many ways you can sort of choose your A, B and choose your f of x, but they will yield the same number in the end. It's different functions over different intervals. So will I get full marks for writing exactly like this, or are there missing things to cover? For this particular question, I know Kathleen likes to sort of split it into two different screens. You would get full marks by doing it like this. You would just because this is an equality you're computing, there's not as much justification as you need, whereas the proof sort of were more heavy on justifications. Here, there's not as many. Like going back to this proof in in question 2, one thing you could have said here is like by definition of indefinite integrals. So whoever already wrote down the solution to question 2, that's one thing I'd add that I sort of forgot to. And also here, same thing, by definition. So in general, in this course, it's kind of like the more justification, the better. You never really want to lack on justification unless you have no time. In the first group, we said xi and I equals 1. But in this one, we have I equals 0. Which one is right? Sorry, where else do we have xi? Oh, you're right. This should be from 1. This should be from 1. Sorry about that. Yeah. The one with 1 is right. So we want our xi's. In general, when you define a Riemann partition, it should be xi from I equals 1 to n. The reason why is because if you think of like a right-hand sum, it will go from I equals 1 to I equals n. We know that on a left-hand sum, it'll start from, it uses I minus 1 instead. So your I minus 1, the minimum I minus 1 you can have here is it 0 or 1? I think it's 1. And then yeah, the minimum we could have would be 0, which would work. I think it's 0. Yeah, it's 0. My bad. I apologize about that. It's 0. And it's sort of like I just kind of re-derived it myself too. A way you can think about that is our sums go from I equals 1 to n. So we know that in a left-hand sum, you'd be using f of xi minus 1. You want that xi minus 1 to be 0. So you know that 0 needs to be accounted for. So yeah, 0 needs to be in your partition. Sorry about that. Okay, cool. Okay, yeah, but like I was saying, for this question, there's not much justification needed. Not much more, at least, because this is a computation. You're just choosing what these things are. You do want to use your correct connectives though. So here, for example, I had choose delta x equals 1 over n. This implies that b minus a is equal to 1, right? So you can't just have this floating. You can't just have it floating like that. You need to say that the above statement implies this one. So use of connectives is a huge one that people lose marks for by just writing things on top of each other without exactly saying how they're connected. So just make sure to be on top of those. Okay, so going back to fix the mentioned mistake, we go to question 1. The partition we defined here should have started at I equals 0. All right, so you guys are the ones currently doing this, so trust your instincts on this, and you'll probably remember it, right? And then yeah. Okay, cool. So any questions about the third one or any of the previous questions at all? Let's give a few seconds. Okay, I assume not then. So this is the end of my part, and somebody else will be taking over for the next set of questions, which are related to Darboux and non-integrability. Okay, thank you all.
Hi, so I'll be taking over. Let me just share screen. So I was planning to use my iPad, but it seems like it's not working right now. Okay. So, okay, let me just, okay, what is this? Here, so I'll be writing the question down. Let me just paste it in here as image instead. What is happening? Oh, sorry for this technical difficulties. So, can someone just share the question, please? Sorry. Hey, excuse me, can you share the question, please? Okay, I'll just be sharing it here. Okay, I didn't expect this to happen with my thing. So first, could everyone just take down a note of this question? So prove that the function, this thing, so let me write it down. So prove so prove, I'll write it down in here. Okay. So I'll just show it up in this slide. So prove that the function f of real to real be defined by f of x is equal to 3 pi over 2 if x is an element of the rational and 0 if x is an element of irrational. So use the Darbo's integral definition to prove the following does not exist. So this was last year's question. I just changed a bit of it. So I think it might be important if you try to take note of this question. So, okay, e sine f of x dx. So I would suggest first you start with an aside. This is what I have done. So you first place an aside and you try to calculate the values. So there are two values over here, which is 3 pi over 2 and 0. So what I would suggest is doing like an aside and place e sine of f of x for the value of e sine of 3 pi over 2. And then you just try to calculate it. So it's going to be e sine 3 pi over 2 is going to be -1. If you're having a hard time, just try to draw in the exam on the side, like just try and then draw it like this. And then it's going to have pi half over here, pi 3 pi over 2. So it's going to be -1. So it's e raised to -1. And for the other value, just do the same thing. Sine of 0, which is going to be e, which is over here, and the sine of 0 is going to be here, which is e raised to 0. And anything of e raised to 0 will be equal to 1. So right now we see that they both have a different value. So we can use this later on in the proof. So let's first start with the first line of justification that Kathleen always asks us to do, which is to identify what are we supposed to do in this question. Okay, wait, let me just, there. So first, we want to show that the following does not exist. In the Darbo's definition of delta and epsilon, we need to show the inverse of the original statement, which is for all epsilon greater than 0, there exists P of partition A and B such that U of F and P minus L of F and P is less than epsilon. So we want to get the inverse statement of this. So we place there exists epsilon greater than 0 for all P of partition A and B such that U of F and P minus L of F and P. This one is less than epsilon. So anyone have a suggestion on what I'm supposed to do? Why am I not seeing the comments? Okay. Yeah, I don't think anyone's replying, so I'll just write it down. Gradient equal to epsilon. So we start with the statement of all the Darboux integrals, which is let P equals xi. You should write this or else she will deduct a mark for sure. So I equals 0 to n, be any arbitrary partition of 0 and 1. Anyone like having a hard time understanding it, just feel free to message. Let me just check. Yeah. Is this integrability or formulation? Yeah. I'll be doing that one in the next question. So first one, use density and definition of MI. Yes, that's true. And that is the reason why I used why I calculated e raised to -1 and e raised to 0 at first, because I want to get the values of the small MI and the big MI. Yeah, okay. So I'll be continuing it. So given any I equal to 1, 2, up to n. Oh, wait, let me just fix this. This is supposed to be 1. So I have to write the statement and also the statement. They're really important. It's a mark that's going to be taking you a lot. And also, it's really important to write in here that let g of x equal to e sine of f of x be a composition function. The reason why we had to define it was that we had this entire function and it was a composition function because f of x was like inserted into e sine of x, and then we got this composition function over here. Does anyone have a like hard time understanding it? Feel free to message, like I'll be answering your questions. So you need to place this statement that is really important before you start on to getting the MIs. So we write MI is equal to infimum of g of x such that x is an element of xi minus 1 and xi. Where did the sign come from? Okay, so when you can see the question over here, we have e of sine of f of x. So we're just using the question, which is written over here. It's not just f of x that we're getting using for this function. So it's e sine of f of x. Does it answer your question, Maya? Okay, that's good. So I place in here mi is equal to infimum of g of x, such that x is the element of xi minus 1 xi. And it's important to follow with a statement. By definition, for I equals 1, 2, up to n. And also, it's because as it is dense and real. So we have e sine of 3 pi over 2 and e sine of 0 for rational and irrational. So you might be wondering, where did this come from? So you can check out this aside I placed over here. So as you can see in the side, I had e sine of 3 pi over 2 that I wrote in here for a purpose. And I had e sine of 0 of e raised to 0 is equal to 1. And this was for the rational. This one was for the rational. And this was for the irrational portion. Instead of writing g of x, can we just do mi is equal to, yeah, that's okay, but I mean, it's better to, since we already defined it in this portion, that g of x is equal to e sine of f of x. So it might be better to just write it as like g of x, because that's how usually she writes it in class, but you can also write it that way. It's much more easier seeing it that way. Yeah, that's true. You can also write it that way. I don't think that will deduct any marks, obviously. So using the values that we obtained from the previous portion, we get the infimum and the supremum. So the infimum will be the values. What is the values over here? It's 1 over e and 1. So you place in here infimum of 1 over e and 1. And since infimum takes a smaller value, so 1 over e is obviously going to be smaller than 1. So you just place 1 over e. Then we try to get the big mi, which is defined as supremum g of x, such that x is an element of xi minus 1 and xi. So by definition, for I is equal to 1, 2, up to n, as it is dense in real. It's important to place that it's dense. That's the reason why it's like this. And then we place the same thing over here again, e sine of 3 pi over 2, e sine of 0 for q and irrational. So here again, we have supremum, 1 over e and 1. So what's the bigger value in here now? It's going to be 1. So we place in here 1. And let's go into getting the L of GMP and and U of GMP. So L GMP is equal to the definition, which is the summation of I equals 1 up to n of the big mi xi minus xi minus 1. And it's important to place here by definition. So what do we know about the value of mi? So over here, we wrote in here, it's 1. Is it required to write? Yeah, it's required. I remember she deducted marks because we don't write those stuff. So yeah, I suggest you place that. There's so much deduction of marks that can happen. So I suggest that you place everything down because you'll be more safer that way. So in here, you place the mi, which is the value of 1. So 1. And then it'll be the summation. I equals 1 n xi minus xi minus 1. So this one, we know that xi and xi minus 1, we can look back. What are they actually referring to? It's a partition of 0 and 1, as you can see over here. So we use this 70% of the difficulty A37. Yeah, that's true. Yeah. Okay, so we can look over here that it's a partition of 0 and 1. So we use that to calculate the rest. So we write in here 1 times length of 0 and 1. 0 and 1. So it's just gonna be 0 and 1, so it's just 1 minus 0, so it's just 1 over here. So we got this value. So let's go to the other side. Does anyone find this confusing? Don't we use mi for the lower Darboux sum? I remember using this one.
Um, since it's the lower Darboson, isn't it supposed to be 1/e instead of 1?
Wait. Because I remember writing this, and that was how it was checked on the paper. Does anyone also have other objections? Yeah, don't we use MI? Okay. So I think, yeah, MI. I think I just wrote it wrong. Okay. Yeah, but it's the same result. So MI, so it's just going to be the small mi, so 1/e. Sorry. Okay, so let's go on to the next one. So GMP. And then this one will be equal to the big one this time. So by definition. So as you can see over here, the big mi is going to be equal to 1. So we place 1 summation I equals 1 up to m xi minus 1. And then you write in here that it's going to be 1 times length of 0 and 1. As stated in this first portion of the question, is a partition of 0 and 1. It's a closed interval. Let me just make it more clear. So, okay, 1 times 1. So it's going to be 1 over here. So now we have to do the conclusion. So I'll place it over here. So since P is an arbitrary partition infimum of U G and P such that P is an arbitrary partition of 0 and 1. And we can see what that value is over here. That is equal to 1. And supremum L of G and P such that P is an arbitrary partition of 0 and 1. This one is equal to 1/e as infimum upper G and P such that P is an arbitrary partition of 0 and 1. This is not equal to supremum L and G and P such that P is an arbitrary partition of 0 and 1. Okay, there. So this concludes that this integral of 1/0 e raised to sine of f of x dx does not exist. So I'll zoom out here. If anyone has questions, you guys can ask in the chat. Okay, so I think there's a mix of integrability. Yeah, it is. The one to show part is using integrity reformulation, but we are asked to use Starbow's definition for this question. Yeah, so that's why I just placed these because we'll also need this later anyways. So this one is basically for Darboux definition, and we'll also be having this integrability reformulation in just 1 minute. Does anyone have a question regarding this? Because like, do you want to take a screenshot? We just have the one to show this portion. We're going to be using it in just 1 minute. So this portion, we're going to be having this to be used in like just a few minutes. So yeah, wait, other questions? Yeah, I did. I placed in here, oh, the one to show. Yeah, that's true. But I already placed it in the bottom of the portion over here, if you're confused. So this is the final conclusion. But let me just paste that portion, this one on the side. Yeah, that's true. So we'll be using this later on. So yeah, let me just go over it one more time. So we have this function of f of x equals 3 pi over 2 and 0 for irrational, irrational, and we want to use the Darboux definition to prove that this does not exist. So I did an aside to get the values when f of x is equal to 3 pi over 2 when it's rational, and when it's going to be 0 for irrational, and I got the values of e raised to -1 and 1 for each of them respectively. And then I started with the important line of that we always have to put that let P be an arbitrary partition of 0 and 1. So given any I equal 1 to n, this is what we want to show, that this is the g of x is not going to be integrable. So I defined g of x to be a e sine of f of x. And it's important to place in here that it's a composition function because it's using the f of x and placing that value into e sine of x to get e sine of f of x. So, okay, and over here we got mi, which is the infimum of the g of x. So we have 1 over e and 1, which is going to be equal to 1 over e. And it's important to place this line over here that it's dense and real. That's why it's going to be these two values. And similarly, the big mi that we got, which is the bigger one among 1 over e and 1. It's going to be 1 over here. And then the L of G and P, we use it by definition. So we got the small mi, and we got the length of 0 and 1, similarly over here. So by the Darboux definition, since the infimum and supremum does not match, it means that he might be running behind time. Oh, okay. Oh, sure. Yeah, I'll be continuing it. Thank you. Okay. If you have any questions, you can just message me directly, but let me just continue because it seems like I'm running out of time. Okay. So since this one over here, I already wrote down the definition for integrability reformulation, and let me do a question regarding it. Does anyone need me to like repeat this? Because I think, yeah, I'm running out of time. Okay. So let me write down the question. So prove g of x is equal to 0 and -e if x is an element of Q, if x is not an element of rational, is not integrable on A and B, where A and B is an element of real, use the integrability reformulation definition. Which is the statement above, that's directly over here, there exists epsilon greater than 0. So since we need to find a specific epsilon, choose epsilon is equal to something greater than 0. We can just figure it out over time. So let's dive into the proof. So let P equal xi, I equals 0 to n be an arbitrary partition of A and B. This one is because for all P, an arbitrary partition of A and B, so I wrote that statement down. Now we need to get Mi, which is equal to infimum of G of X, such that X is an element of Xi minus 1, Xi by definition. So we are getting the smaller values, and there's 0 and negative E. So it's coming from here and here because rational and irrational are dense in real. So we have infimum of 0 and negative E. We need to get a smaller value, which is obviously the negative E, and the big Mi this time, which is going to be supremum of G of X, such that X is an element of Xi minus 1 and Xi by definition. So we have 0 and negative E because rational and irrational are dense and real. So we look back. What are we supposed to prove? We're supposed to prove that this one is going to be greater than equal to epsilon. So we use the definition again. So upper of F, G, and P, U of G and P minus, what is it again? It says L of F and P. L of F and P, G and P, oops. G and P. This one is gonna be equal to the summation of I equal 1 and Mi Xi minus Xi minus 1 minus summation of I equals 1 to Mi Xi minus Xi minus 1 by definition. So now we have to sub in the values. So we have negative E for the small mi and 0 for the big mi. Wait, let me write it here. So supremum so this one is going to be 0. This is going to be negative E by definition. We have above I equals 1 and 0 Xi minus Xi minus 1 minus I equal 1 and negative E Xi minus Xi minus 1. So these are constants. We can take it out by summation properties. I go 1 up to n, 0 plus E, because it's minus E. So, and then summation of I equal 1 to n of Xi minus Xi minus 1 by summation properties. So it's going to be 0 plus E. This one is Xi minus Xi minus 1. You can see over here it's from A and B. It's a partition of A and B. So we place in here, it's going to be length of A and B. And it's going to be E raised to B minus A. So we look back. What are we supposed to prove? We're supposed to prove that it's greater and equal to E. A good epsilon that we can place over here is greater and equal to this value. So we can make this value, this E of B minus A, into epsilon because anyways they'll also be equal. So we can place in here, just choose E epsilon as E of B minus A greater than 0. We know that it's going to be a positive because E is going to be positive and B minus A is going to be greater than 0, and B is going to be greater than A. So yeah, because of this A and B over here. Anyone have any questions regarding this proof? I think the integrability reformulation questions are just like they're really fixed in terms of the format. Any questions, anyone? Okay. Is there a sum for okay, can you go up for a bit? Okay. Is there a sum for both 0 plus E and xi minus 1? What do you mean, is there a sum for both 0 plus E? I wrote in here, over here, the end. Yeah, I placed in here, it's gonna be 0 plus E. This entire thing is the length of A and B. This summation of this portion over here. Let me just highlight it. So this portion over here. Oh, wait. Why is it going that way? Undo. Okay, I can't undo it. But basically, this portion that you see over here, the summation, it's gonna be length of A and B. So it's gonna be this thing, and you just have to subtract it. Do you have like, is there anything specific? You can just unmute, Vilma. And there, if anyone wants to take a screenshot. I was thinking of keeping one sum sign. I was jumping steps. Oh, okay. I think it's better to just keep it that way, and yeah, I don't think it's best to skip steps, honestly. Like she might be questioning why it's gonna be like that. I think it's really important in 837 to not skip steps. Okay. So any questions regarding this Darbo, like the other one, number 1 and number 2? Like should I like zoom out? Is this okay for everyone? Okay. So I think if there's no other questions, just feel free to message me if there's like, can you share this page? Okay. Wait, how do you want me to share it? I think we'll be sharing it in the end of the meeting. But yeah, so let's let the next person take over.
Hello, hello. Can you guys hear me?
We can hear you.
Okay. All right. So I'm gonna go over these two integral questions. And yeah, let's start with the first one. So here we have the integral of 2 over x cubed minus 2x squared minus 2x minus 24. And any ideas on what the first step is? Okay, so divi set PFD. And yeah, in general, if you see a rational function, which is some polynomial over another polynomial, and the denominator is a higher degree than the numerator, then you can directly apply PFD. So our first step will be applying PFD. So here we're taking the integrand, which is 2 over x cubed minus 2x squared minus 2x minus 24. And our first task is to factor the denominator. To factor this, you can check, you can do long divisions and check if it factors with any of x minus a factor of 24. And here, it just happens that the denominator factors into x minus 4 times x squared plus 2x plus 6. If you want to verify this, again, you can do long division. Yep, so here we have x squared. You'll get x cubed minus 4x squared. You have 2x squared here, minus 2x. You have plus 2x. And you have 6x minus 24. You have plus 6 here, and you have 0, and you're done. So that's the first step. And here, the quadratic term, x squared plus 2x plus 6, has a negative discriminant. So we can check that the discriminant equals 2 squared, b squared minus 4ac. So 4 times 6 times 1, which is 4 minus 24, which is negative. So this term cannot be factored anymore. So here we already factor it to the absolute maximum. So I see a question in chat, why did we divide by x minus 4? Yeah, we need to factor the denominator here. And to do that, you want to guess and check by dividing by a linear term of x minus some factor of the constant term right here. So if you were to do this in the test, you will guess and check from x minus 1, then x minus 2, x minus 3, x minus 4, and so on. Right, now that we have factored the denominator, we can move on to actually doing PFD. So the first factor is a linear term, so you will have just one term in the numerator, and the second term is quadratic. So you'll have bx plus c in the numerator. Only one real root is evil? Yeah, it is. But this is, I think this is like a fair question that can come up. So yeah. So here we cross multiply to get the common denominator, and we'll get a times x squared plus 2x plus 6 plus bx plus c times x minus 4 equals 2. Then we can distribute all these terms and get ax squared plus 2ax plus 6a plus bx squared minus 4bx plus cx minus 4c equals 2. And then we will group them up by the degrees of the x's. So here we have ax squared and bx squared. So we have a plus bx squared. We have 2ax, 4bx, and cx. So we have 2a minus 4b plus cx. And lastly, for the constants, we have 6a and minus 4c. So we have that. And this is all equals to 2. So here we have a system of equations. A plus b equals 0. 2a minus 4b plus c equals 0. And 6a minus 4c, oops, sorry, 6a minus 4c equals 2. And here you can solve this whichever way you like, if you want to do linear algebra or you want just to do algebraic manipulations. Here we can notice that b equals minus a, and then we can substitute this result into this equation. So 2a plus 4a plus c equals 0. So 6a plus c equals 0. So you can grab this equation right here with this 6a plus c equals 0 and 6a minus 4c equals 2. We can subtract them and get that 5c equals negative 2 and c equals negative 2 over 5. Then we can plug this into this equation right here and get 6a minus 2 over 5 equals 0. And by some algebra, we get that a equals 1 over 15. And to get the value of b, we can substitute a and c into this equation. And we get the 2 times 1 over 15 minus 4b plus negative 2 over 5 equals 0. So minus 4b is equal to 2 over 5 minus 2 over 15. And this is equal to 4 over 15. So we get that b is equal to negative 1 over 15. So here we have our values of a, b, and c. And we're done with our PFD. Any questions so far? If not, we can continue.
Wait, hold up. I think some people might want a break.
Oh,
So can I just get like a vote in the chat right now? Who wants a break? Who wants us to continue?
break.
I think the consensus needs a break. So let's give them until 4:40. Does that work? 4:40. Yeah, let's give them until 4:40. All right. Uh,
Uh,
does this end at 5? No, this
this
ends at
ends at
6.
6.
All right. So let's just give them a break now and we'll see you guys at 4:40.
Hello. So it's 6:41 now. And yeah, let's continue. So now that we have our values of A, B, and C, we can plug this in into this equation right here. We had A equals 1/15, B equals -1/15, and C equals -2/5. So plugging them in, we get 1/15 over x minus 4 plus -1/15x minus 2/5 is equal to the original integrand. And we can simplify this further. So 1/15 times 1/x minus 4 minus 1/15 times x plus 6 over x squared plus 2x plus 6 is equal to this guy. And hence, the original integral is equal to the integral of 1/15 1/x minus 4 minus 1/15 x plus 6 over x squared plus 2x plus 6 dx. Right. So now that we're done with the PFD steps, do you guys have any ideas on what's next? Factor out 1/15. Are we doing other questions after the second integration questions? Yeah, we still have a couple more sections left after that. Yeah, we can certainly factor out 1/15. We can also go further by splitting up this integral into two integrals. Sorry. Using integral properties, you get this is equal to 1/15 times the integral of 1/x minus 4 dx minus 1/15 the integral of the rest of the terms right here. Now that we have two simpler integrals, so this is by integral properties. We'll first look at this one right here. So we consider this guy. Guess the antiderivative of 1/x minus 4. Okay, yeah. So by inspection, we can get the integral is equal to ln x minus 4 plus c. Shouldn't it be x minus 6 instead of x plus 6? Oh. Did I make a mistake somewhere? No, I think that's right. Sweet. Here we're factoring out -1 over 15. So when we factor out -1 over 15, both terms becomes positive. And yeah, this should be okay. Yep. I'll label this C1 for some real number C1. So this is our first integral. And next, we'll consider this integral right here. Oops, what happened there? Okay. So the first thing that you should notice with this integral, this is a rational function. But again, as we said before, x squared plus 2x plus 6 cannot be factored out anymore. So PFD won't help you here. But you can notice that the degree of the denominator and the numerator only differ by 1. And you can notice here that if you differentiate the denominator, you'll get a linear term, 2x plus 2. So the numerator is a linear term, and the derivative of the denominator is also a linear term. So there might be some way to cancel them out, to do a use up. But the problem here is that you cannot cancel x plus 6 and 2x plus 2 because they are not only different by a factor of a constant. So one idea in the chat is to split the integral. And what are you thinking of? How do you think we should split this? Okay, great idea. So the comment was to split this integral into these two fractions. And this will be, and here we can split the integral using integral properties. Forget the dx there. And let's first consider this one first. Magically spawn a 2. Yeah, that will work. Yeah, they multiply by 2 over 2. Why did we choose x plus 1 and 5? So here, you can notice that the derivative of the denominator is a linear term. And it is 2x plus 2, or 2 times x plus 1. And we want this derivative to cancel out in some way with the numerator so we can do a use up. So that's why we want x plus 1. Yeah, so we'll continue. Yes, some of you guys said we can multiply by 2 over 2, but I'll just do this. I'll just do the use up first. That u equals x squared plus 2x plus 6. So here we get that du is equal to 2x plus 2 dx, which is equal to 2 of x plus 1 dx. And you can rearrange some terms here. So half of du will be equal to x plus 1 dx. And plugging in the u sub, you'll get this is equal to the integral of half times 1 over u times du. And you can do this by inspection, and this should be a half of ln absolute u plus c2 for some c2 in real by inspection. So we still have one more integral left, which is, where is it? This one right here. So there's a comment in the chat saying to complete the square. And yeah, that's pretty much the right idea. You need to, you want to complete the square of the denominator. This will be x plus 1 squared plus 5 of dx. And the reason why we're doing this is because this looks very similar to the derivative of arctan, which is 1 over x squared plus 1. The difference is only here we have a 1 and 5, and also here. But we can do some manipulations to get rid of them. So what I'm gonna do here is to pull out the 5 from the denominator. We can cancel this out. And we can pull the 5 into the square right here. So this becomes x plus 1 over square root of 5 squared plus 1 dx. And now this looks even more similar to the derivative of arctan. So now all we have to do is to do a u sub by letting u equal to the square term right here. We get du is equal to 1 over square root of 5 dx, or dx is equal to square root of 5 du. So this is equal to 1 over u squared plus 1 times square root of 5 du. And by inspection, this is equal to arc tan of u times square root of 5. I'm just gonna put it in front. Plus C3 for some real C3. And this is by inspection. We can solve this by inspection also, I believe. Which step are you talking about? The 1 over u squared plus 1? Without letting u. Oh yeah, you can certainly do that also, if you're comfortable with that. But Yeah, a U sub also works, and but doing an inspection from here also works. Right. So here we can substitute back the value of U. So this is equal to square root of 5 times arctan of x plus 1 over square root of 5 plus C3. So, oops. Here I forgot to put the U back in. Well, okay. You can just put x squared plus 2x plus 6 here. And I think we're done with all of the smaller integrals. Any questions so far? If not, we can just plug the integrals, the soft integrals back in. Here we have this equation right here. So this is ln of x minus 4 plus C1 minus 1 over 15 times the split integral and plugging the values of the soft integrals again. We get this term right here. Plus this arctan term. And yeah, we're almost done. We just need to simplify this term. And let's just group the constants at the end here. C1 minus C2 minus C3. And we can group the constants into 1. By letting this term to equal to C. So you'll write where C is equal to 1 over 13 times C1, C minus C2 minus C3, which is still in the real numbers. And yeah, this is our final result. Whoa, what happened? Okay. Any questions? Comments, concerns?
Bobby, are you gonna do this integral?
Yeah.
I don't think we have time for that because look at the time, it's like 5 p.m. and the meeting and this review seminar is gonna end at 6. We have like, yeah, we're not even halfway, I think.
Yeah, then yeah, but I think and we're gonna post. I think we can post the solution at the end, right? Like at the end of the seminar.
Uh, yes, if you guys get the solution, then I'll put on the latex and post it.
Yeah, okay
Post it
then.
in the AMACSS group.
Yeah, since we're very tight on time here, we'll put the solution of this question in the solutions later. And yeah, I'll let the next person's take over. Thank you.
Right, if that's the case, let's go on to the next topic. I'll be going kind of quick because we're running out of time, unfortunately. Let me share my screen. And also, I might not be able to see the chat, so just like pause me anytime because of a question, but I'll be going kind of quick. No, not this device. Sorry, guys. Let me open my iPad. Correlation matrix, oops. Share my screen, broadcast. Right, you should be able to see my iPad right now. Nice. Right. I'll be discussing the FTOC2 kind of questions. We have 2 questions prepared for you. Let's start with the kind of easier one first, but I just want to show you like the theory behind it. So it lies on the basic of FTOC01, and then like if I wasn't mistaken, it was an Eddy accumulation function of whatever function that is on a certain interval, on a closed interval. So I believe you guys already have this lecture notes from Kathleen's lectures. Yeah. So let's just keep going, okay? I assume everyone understands the theory behind it. Let's just go directly to solving the first question. Let me see. Right. So one important thing that Kathleen really likes is a bunch of justifications. And for FTOC2 kind of questions, she wants us to actually like display one by one. So in this case, I could see this function as like this. Okay, so we can like sort of put them down in the denominator because we have a power to the -1. And then from there, we want to identify what's the function inside. So we'll start with our first line is let our function t become that thing in the inside. All right. And then you observe that the function t is a quotient function containing, first thing, on our numerator, we have an exponential function. And just by normal math intuition, exponential function is continuous on its domain. Which is R, okay, just the domain of real numbers. And our denominator, sorry, I'm writing kind of because we're running quick. We have 1 plus t to the power of 6. We can call this as a polynomial function. And again, it is continuous on its domain. Special attention must be put on the denominator. We know that denominator cannot be 0. Denominator. But we know that for any t, this thing is more than 0. Okay? Because this one, its lowest margin is 0, but we have a 1 plus in here. So it's like always not 0. It's never 0. So all good. Nothing happens over there. In particular, that function is continuous on common points of continuity. Which is, I take that, and I take that, that becomes R again. Okay? I forgot if this is like the correct way of writing it. Anyways. Yeah, it should be and. It should be an and, not an or. So, and what comes next is... And then we also know that this thing is continuous on the limits of the integration, which is the negative of e to the x until 2x to the 4 plus 1, because whatever that is still inside our common points of continuity, which is just the real. Then we can start our writing FTOC2 sentence. By FTOC2, we can define the capital F ranging from C to X, where C, or any constant, is contained inside that interval. And again, that interval is still a part of the real domain. Okay? Note that we can split the original function t with union interval. So what happens is, there's a common practice when you are using FTOC2, usually like your integration limit here is 0. Or it could be actually any other like constant as long as it's like your function is continuous within that interval. So, but in this case, like we don't want to directly put it that way because you'll see later when we break it down. Anyways, I could split it like this. First thing is this goes until C. And the other one from C to the other integration limit. And the justification for this is by union interval property. If there's like the more proper sentence, please write that one. I kind of forgot. I took this course last year. And then I don't want the C to be at the top because that thing usually is in the bottom. So we can flip that by another integration property. That means if we flip the orders of the integration limits, we need to put a negative sign in front. There you go. By some integration property, I forgot. By some definite integral property or something, please write it properly. Now, if you recognize in here, we already have sort of a good format that replicates our FTOC2 sentence. In that case, our x, or like the function inside, for the first component is the negative e to the x. And for the second component, we have 2x to the power of 4 plus 1. So, we can write further like this. And in this case, it will be easy to like just straight away find the derivative. And this is by FTOC2, which is from here. Okay? So if we try to find the derivative of both sides, that means our first component here, it will be f, and the function inside is e to the x. What happens is the entire derivative for this is like this, and then there's like a multiply by -1, right? But then that -1 get canceled out by that thing in front. So we just have like a normal positive f of e to the x, I hope that part you guys understand. And then for the second component, we have this thing, but then by chain rule, we have this, okay? I forgot what's the justification for this one. I think this is just like a by differentiation rules. And I guess you guys are safe writing it until that part. What comes next is just to convert it back to our original function t, our original function f, I mean. This, you can put it in here, and the same goes for this one, you can put it here, okay? So it's just the art of rewriting them. In that
Oh,
case,
sorry, you forgot to chain rule the first term. It's supposed to be f of e to the x times e to the x.
the negative sign gets canceled out by this, no?
But then by chain rule, you need to multiply by e to the x.
Oh, shoot.
And it's f of negative e to the x.
Hold on. F. My bad, bro. Is this what you're trying to say, or
Yeah, it looks
like this, right?
yeah like that.
Right. Okay, so what happens next is... Oh, right. My bad. What happens next is we just need to rewrite them back. In this case, for our first component, we have our exponent negative e to the x over 1 plus t. But then the t is to the power of 6, right? T to the power of 6 is a positive power, so the negative is gone. And don't forget, we still have this, so we gotta like write it somewhere here probably. And then the other part, we have like this over 1 plus, replacing the t. But then we also have this, so don't forget to write that. And that will be our final answer for... There you go. Okay. Hopefully this question is good enough. There's a question. I'll keep going to the next one. All right. No questions. I'll go to the next one. All right. This is an interesting question because instead of actually trying to find the integral or something, but we have to find the integration limit. So it's like a reverse engineering. This is an interesting question. Let's get started with this. So I'll just start first by defining this as our equation 1. Okay. What we can do is we can define another function inside it. Let's call it the function g. The function g contains the thing inside. Okay. Notice g is a quotient function again, containing our numerator is just f of u, and this f of u is continuous on positive values. Okay, it's already given in the question. Right? And then our denominator contains u squared. U squared is a polynomial function, and hence it's continuous on its domain, which is just a real. Okay. However, denominator cannot be 0, so u cannot be 0. Okay, because when it's 0, then everything fails. And then the function g is continuous on common points of continuity. That will be the first one, we have positive. And the second one, we have everything except 0. So what happens is, I think we can write it this way. All right. If I simplify everything here, that means our final common points of continuity is just the positive value. Okay? So in particular, GU is continuous on the integration limits because we're heading towards FTOC2. And this is good enough because, I mean, we can, in the first stage, assume D is still contained within this thing. Okay? Right? By the way, this interval comes from the integration limits. So we're done with like those steps. We can apply FTOC2. Let's define the function capital G. Where D is just some real number, but the real number has to be positive because of this restriction. Okay. I could easily differentiate both sides immediately. So let's go differentiating both sides of that big equation in the beginning. That means our 6 becomes 0. Then the second component will be the interesting part that we'll handle. But actually, this becomes gx already because we replace this by our definition of g in the beginning. And for the second part, there's a 2 root x. The derivative will be something like this, but we still have 2 in front, okay? That simply crosses out. And simply, the derivative of a function capital Gx is the big G with that apostrophe thing. But then by FTOC2, we have this definition. Capital G derivative is equal to the small g. But then I know at the beginning, I defined g as that function. Okay, so let me drag a big arrow over there. What happens is I can replace g to its definition in the first place. This is by definition of g. And so if you switch things over, our function x is x to the power of 3 over 2. And this is still good enough because we have a square root in there with the over 2. And for a square root, x is still within the positive values just to satisfy this restriction. So everything is good. Then we can go back to our original question. That means, oh, I need some space, I think, here. Okay, this is because I already find my function f. My function f is this, so I can replace it to our original equation. Just replace it in terms of u. Okay. And then I can simplify this form becoming negative half, okay? And then by inspection and FTOC1, where I solve it from u, these are the integration limits. So what happens is, this is just by algebra, right? And this is by FTOC1 or inspection. I forgot how you should say that thing. What comes next is, this is the final simplified version. And after switching things over, I found out that my square root of d is 6 over 2 or 3. Therefore, my d is 9. And that is a good answer because 9 is a positive value and it doesn't violate the condition or the restriction that we put at the beginning. All right, I'm zooming it out for you guys to take a quick screenshot. If you guys have any question, please directly raise up your hand. Otherwise, we'll directly move to the next topic. Right, we'll wait for some more few seconds. Oh, thank you for, thank you for those people who helped me answering something on the chat. Right, since there's no one else, I guess that's all for my part. We can continue to the next person.
Okay, hey everyone. Let me just share my screen. Can you hear me?
Yes.
Cool. Okay, can you see my screen?
Yes.
Okay, so the question at hand is the integral of x cubed ln of x squared plus 1 dx. Okay, anyone have any ideas about what to do? Oh, I can't see the chat. Okay, you solve with, okay, perfect, yeah, that works. So let me get a different color. Let u equals x squared plus 1, and then this implies du over dx is 2x, right? So which implies du over 2 is x dx. Okay, this is u sub. Okay. And then, so where exactly does x dx show up in this integral so that we can substitute du over 2? Okay, perfect, yeah. So this is, you split it into x squared x ln x squared plus 1 dx. This is by just exponent laws. And then, so you have this is your u, and then this and this is your du. So this is just equal to, oh, my bad. And then you have the x, yeah. Okay, yeah, perfect, okay, yeah. And then you have the x squared, because here you said we said that u was x squared plus 1. So from here you get that x squared is just u minus 1. And then we have to substitute it into here because we do not want to mix variables and use substitution. That's the most important thing to remember when you're doing u sub. So you have u minus 1, and then the x and dx get absorbed into the du over 2 ln of u du. Du. Okay. So now you have two options. You can either just write it as a sum, u ln u, I'm sorry, as a difference, minus integral ln of u du. This is by integral laws. Oh, I forgot the 1 over 2. Actually, let me write it in here because we have to justify that we can take it out, right? So this would be 1 over 2, the integral u minus 1 ln of u du. this is by integral properties. Integral properties. 1/2 constant. Okay, so you can either split them or just do it directly. You treat u minus 1. This is just a polynomial, and then you have ln of u. So someone in the chat mentioned that we proceed with integration by parts. So what would you let your, since I've already used u, I'm going to use dv and w. So what would you let your dv and what would you let your w be? Okay, perfect. What would you let w be ln of u? Why not u minus 1? What's stopping you from? Exactly, perfect. You want to differentiate ln of u. So you do this, and then because if we let dv ln u, that would be problematic because we don't really know the integral of ln of u, and then you'd have to do another integration by parts, and it's just like circular reasoning, so it doesn't make sense. So w is ln of u, and dv is everything that's not ln of u would be. I know it's error, but no, but not. Yeah, unless you wanna. Yeah, perfect. So dv would be everything that's left, which is, oh, that's the wrong color. My bad. U minus 1 du, right? So from dv, we get that this is v. Yep, you're going to integrate this, right? So you get v is, what's the integral of u minus 1? It's just u squared over 2 minus u, right? And then for w, since you're going to differentiate this, you do, and you're differentiating with respect to u, dw over du is 1 over u, which implies dw is 1 over u du. Okay, so we're going to use, so by integration by parts, you know that the integral of w dv is just going to be wv minus the integral of v dw, right? This is integration by parts. Oh, that's not by parts, my bad. By parts. So we're going to use this dw and we're going to use this, okay? So wv is just ln of u, and v is this, right? U squared over 2 minus u, and then you have minus the integral of v du, which is u squared over 2 minus u, and our dw is just 1 over u du. Okay, and then, okay, I keep forgetting the 1 over 2. This is, okay, actually, I'm just gonna add the 1 over 2 at the end because I haven't included them in my dv's and w's. So this is just, unless you want to guys, okay. So this is just 1 of u squared over 2. Not my bad. U squared minus 1 of u. This was not really necessary. I don't know why I did it. Anyway, and then here in this specific term, you can cancel the u's from here and here. So you get minus the integral of u over 2 minus 1 du. Okay. Any questions until this step? Okay, I'm just going to proceed. So we get this is equal to, to save time. And then the integral of u over 2 minus 1 is just, because by integral properties, this would be the integral of this and the integral of this. So this would be u squared over 4. Well, it's 2 times 2 because you have the constant plus u, right? And then you can add the plus in here. So this is integral loads. I used some of linearity of integration. Linearity is what I use here for being able to split these two terms and for considering the constant on its own. So this is what you have. And then you have to remember that this was a u sub, so you have to substitute your u value again. So this would be ln of u. I'm going to just factorize it by taking the common factor outside. U over 2 minus 1. And this is just minus u over 4 minus 1 plus c. And your u is just squared plus 1 times x squared plus 1 minus x squared plus 1 minus 1 plus c. Okay. Anyone have any questions as to what the last few steps? I'm the one over here, so forgot it. This was just for this part, and then you have just add a 1 over 2. I don't have space in here. Let me just add a page after. So the final answer would just be 1 over 2, and then this whole thing. You can technically not include plus c because 1 over 2 times c is just a new constant, so it doesn't really matter. Ideally, you just add it in the last step, especially when you're doing integration by parts. Because if you keep adding constants at each indefinite integral, you're just going to get like a bunch of constants, and then in the end, you're just going to absorb them into one. So any questions so far? Okay, cool. So just like what you take away from the specific u sub is that your u sub is, it might be very apparent in this case because the function inside the u, inside the ln argument, we had x squared plus 1, and it would have been like, you could have easily just said why not just let x squared equals u, or like x cubed or something, but you want whatever you differentiate to come up again in the integral. So just like keep that in mind. Cool. So the next question's kind of okay, anyone have any ideas about what to do here?
Oh, sorry, we're very tight on time. We
Yeah,
should
okay,
probably just do it.
Okay, cool. It's not okay, cool. So you have complete the square in the numerator. Okay, that's something, but that would take longer. So you have x squared plus 1. Okay, don't like it now. X squared plus 1 e to the x over x plus 1 squared dx. So this is just, you can just add a convenient 0. So this would be x minus 1 plus 1 plus 1 over x plus 1 squared e to the x dx, right? And then what you can do here, this is just add 0, and then this is just x squared minus 1 over x plus 1 squared plus 2 over x plus 1 squared, and then you have the e to the x dx. This is just technically partial fraction decomposition with like 2 terms in reverse. So it's different from the partial fraction decomposition for the integrals. This is the algebraic manipulation. So you have, and then this is just x squared minus 1, which is just x plus 1, x minus 1. So you can cancel one of the x plus 1 terms from the square in here. You get x minus 1 over x plus 1, and then you have plus 2 over x plus 1, right? E to the x dx. Okay, and here you can, what you could notice is that one of them is just the one of the 2 functions in here is the derivative of the other function, and that's this function. So if you consider the derivative of this, you get x plus 1 squared, you get x plus 1. We're just going to use the product rule. This is just 1 minus x minus 1, which is just 2 over x plus 1 squared. Cool. So this is just this function is the derivative of this function, and then you have an e to the x in here. So you can technically apply Gegencheck, because you know that if you have f of x and e to the x, use, yeah, perfect, the v. That's exactly what we're going to do. And if you differentiate this, because e to the x has the same derivative, it's just f of x e to the x plus f prime of x e to the x. So that's what's going here. And because we don't have a lot of time, I'm just going to go into the next question. Okay. State the mean value theorem for integrals. Define, and then you have a function, and then you want to find a c that satisfies that function. So, sorry. The mean value theorem for integrals is basically you have to, whenever you're asked to like write a definition, make sure you write every single condition, because there's points awarded for every single thing. So you're going to let a and b be in reals such that a is less than b. So if f is continuous, f is continuous on closed interval ab, then there exists a c which belongs to this open interval ab, such that the integral from a to b f of x dx is just f of c a minus b. Oh, b minus a, which is basically saying f of c equals 1 over b minus a. This has to do with like the average of the function. At some point in your like function, it's going to equal the average. Okay. And then you have to find a c in this specific interval such that mean value theorem is satisfied. So okay. So your f of c. So you're going to actually, because we don't have a lot of time, I'll try to take this over at the end if we do have like some extra time. So we can move on to Eddy's set of questions, because those are true false questions and they're very important for 837.
All right. Can everyone hear my microphone? Sorry, give me a second. I'm trying to share it. Can you guys see the questions? Okay. Perfect. So as you guys may know, in A37, there's always going to be like not multiple choice. There's never multiple choice, but like there's going to be a true false section. So let's start with the first question. I'll let you guys read it. So can anyone tell me if this is true or false? You let f and g be positive and concave down integral functions on AB. Then any trapezoidal approximation will under approximate the integral of their product. Sorry if my background is a bit loud. I'm in Tim Hortons right now. So, can anyone tell me if this is true or false? No answers. All right. So it happens to be the case that this is false. Can anyone think of a counterexample? Actually, I'm gonna just give you guys a counterexample right now. So let f of x and g of x be equal to square root of x. Clearly, I'm pretty sure you guys know this is concave down, right? Would be decrease. Yep. So for these multiple choice, not multiple choice, true false questions, you guys don't really have to make any justification. So I'm just gonna sail with it, and you let this be the case. And clearly, f times g is just a linear function, right? However, let's select a equals 0 and b is equal to 1. Then clearly we know that the area under the triangle from 0 to 1, we know that the area under this curve is just the base times height, correct? So that's just 1 over 2. But we also know by the trapezoidal approximation. Let me show you guys. Let's see. So we know this is equal to 0. And let's just make it an arbitrary partition, right? So x1, x2, xn is equal to 1. If we put all of this into a summation, recall that the trapezoidal approximation is the following. It's I minus 1. This is the area of the trapezoid if we multiply it by the base. I don't know if you guys can see it, but this is essentially the base of the trapezoid. This is the base, xi minus 1 xi. And this is just like, we're taking the sum of this length and this length, it's just cutting in half. So that's the area of the trapezoid. Start 1 all the way to the end. Notice you can simplify this to the summation. 1, sorry, let me clear this real quick so I have more space. And notice you can combine this together. I squared minus I minus 1 squared divided by 2. You can pull this 2 out. So let's move it up here. You can pull this 2 out. Get 1 over 2 summation of this. But note, you can also notice that this is a telescoping sum because it's equal to this. It's the first group. The second group, x2 squared minus x1 squared. And then you guys can see the pattern, right? Xn squared minus xn minus 1. And with every telescoping pattern, you can see that this cancels out with this. And the pattern continues. This cancels out with this. This cancels out with this. You have to justify it. If this ever shows up as a non-true or false question, you have to justify that. And now you're just left with. So let me remove this summation. So you're just left with xn squared minus x0. But can anyone tell me what xn squared is and x0 is? Can anyone tell me? Okay, what is b and what is a? Because remember, we're working with, sorry, my mouse is like tweaking out. Yeah, exactly. It's 1 and 0. Yep, that's correct. So you get 1 squared minus 0, 1/2. Is this an under approximation? No, it's not. So yeah, that's how you would show that this is false. Although on an exam, you wouldn't have to justify anything at all. Next question. I think you guys can read this. So we define f as some arbitrary function from a to b to c to d, and g to be an arbitrary continuous function on c to d to the real numbers. If we compose g of f, and this composition is Riemann integral, then f is Riemann integral on ab. So is this true or false? So we're basically saying that composing any function inside of a continuous function is Riemann. If that's Riemann integral, then yep, that's true. It's false. Sorry, I meant to say it's false. It's not true. Can anyone tell me why it is false? Can you give a counterexample? Let g of x equal to 0. Yes, exactly. Divi gave a pretty good answer to that. So clearly this, and let's say f was equal to the Dirichlet function. So this would be on, I think q, right? No, it should be on not q. Sorry, it is on q. And this is not on q because q is countable. And anyways, so if you compose g of f at x, then, oh, sorry, it's not supposed to be a 0, it's supposed to be a -1. Wait, is it supposed to be a -1? Yeah, it is. Like this. And then clearly this is just 1. You guys agree? Because we're just squaring this, and if you combine the irrationals with the rationals, you just get the real numbers. All over R. Just like that. Sorry. For x in R. as such. However, we know that f is clearly not Riemann integrable because this is just a variance of the Dirichlet function. I'm pretty sure you guys can show this pretty easily, so I'm not going to do that for the interest of time. All right. Third question. Yes, it is true. Can you explain why? Can you explain why it's true, Diddy? Okay.
Oh, let me just unmute myself. It's okay. So x to the n is odd if n is odd. 9n to the minus 1 is odd when n is even, so they can't be both odd. So that means either one of them has to be odd, and the other two have to be even, and that means the product has to be odd.
Yeah.
So it's
that's correct. So the intuition is that if we define f at x, you x at n, sine n minus 1 of x, cosine of. Sorry, this is a little choppy. I'm doing all this writing with the mouse. If we do f at negative x, let's say n was even, right? Let's say n was even, then clearly this remains the same. If n is even, then n minus 1 is odd. But sine is an odd function. So that means we can pull this out here. And then cosine just remains the same because it's an even function. And now notice this negative sign can just be pulled out such. This exponent's supposed to be right here. But you guys get the point. And then you get negative x. I'll leave the even case for n as an exercise for the readers, but it should be equally as Actually, sorry, I meant the odd case for n. So I'll leave that as an exercise for the readers. And I believe this was a question on the assignment. You had something like, if you had the integral of negative a to b, and let's say f was an odd function, right? Then this is just equal to 0. So in this case, is pi f at x is equal to x to the n sine of n minus 1 x cos of x. So this is just equal to 0. All right. Next question. Can anyone tell me if the next question is true or false? Let g be a strictly decreasing differentiable function in R. Then the following function is decreasing in R. Can anyone tell me? Actually, true. Can you explain how you got your answer? Just
so
explain to me what's like the major thing you use to determine
you
it.
take the derivative of the function using FTOC2. If the
Exactly.
derivative is less than 0, it's decreasing.
Yes, so you have to realize that the function inside here, let's call this h at x. It's pretty much continuous everywhere in R, right? So that means it's continuous on any AB. It doesn't really matter. So let's say, so we can just say it's continuous on 0 to G. Therefore, we can apply FTOC1. So define f at x equals 0 to x. H at t, not h at x. H at t dt. All right. Now, what is f of g at x? This is just simply the integral of from 0 to g of x, h of t, dt. All right. And then we can just differentiate it if I can find my mouse. Okay, let's differentiate it. So we get df of g versus respect to dx. And that's equal to simply f prime with respect to g prime of x. How did I get this answer? Chain rule. You get this through chain rule. So, and what you can do from here is that you can realize g prime is less than 0, right? Because we said originally that g was a strictly decreasing function. How about this? Recall from FTOC1, this is just simply, correct me if I'm wrong, it's this, correct? Is that correct? Yeah, I think it should be correct. And then from here we can just bring everything together. Notice this function is positive. This function is positive, but this function is less than 0. And recall this, we're taking the derivative of this whole entire function. And we found that this is less than, actually it's less than or equal to 0 for all x in R. And what does that say? That says that this function is decreasing in R. So yeah, you would get a question like this in your exam. You could get a question like this in your exam. It actually showed up before. And yeah, let's move on to the last question. All right. So let A, B be real numbers such that A is less than B. If f and g are continuous function on AB that satisfies, they have the same integral on AB, then there exists an x in AB such that the functions are the same at x. So is this true or false? Yes, it is true by MVT for integrals. So how would you go about showing this? Sorry, give me a second. So you would show this by, actually, first of all, how do you know you can use MVT? Yes, exactly. You define h of x. Subtract both sides and same answers. Yes, exactly. But how would you know that you can use MVT? What's the condition of MVT that allows you to use it? Let me ask you this. What f and g are continuous on AB? That's correct. And then when you take the difference of f and g, that's still continuous on AB. So now what you can do is that you can use NVT to say there exists a C such that this holds. Yes, exactly. And I believe it's from A to B. F x dx, just like that. And now simply, oh, where's my mouse? We know that you can split this up into A, f at x, dx, d of x dx. And can anyone justify why we can split this integral? It's an integral property, but can anyone explain why? By linearity, that's going to give you half a mark. You need to justify that f and g, since they're continuous, then they're integrable on AB. So you can indeed apply the property of linearity, all right? But we know that their integrals are basically the same. So you can, so this is just equal to 0. F minus g of c. B minus a is equal to 0. However, we said that a is less than b. So b minus a is greater, strictly greater than 0. What does that mean? You can just divide it out. You get f minus g, c equals 0. This brings us to f at c equals to 0 c. So yeah, it's true, true, true. And I think both of these were false. And yeah, I guess that brings us to the end of the review seminar. Does anyone have any questions? Any questions like related to the exam rather than just the questions? What's your favorite integral? I like the Lebesgue integral. That's pretty nice. You should definitely read into measure theory. I think I was about to post like a recommended book for you guys to study the Darboux stuff, but then I figured it was too advanced and I didn't post it. But you guys should check out. Let me type in the chat. Chapter 1A. Chapter 1A has questions related to the double stuff, and I think it's pretty feasible. One of you guys review seminar questions from your TAs involved one of the questions from there. So you guys should definitely check out that textbook. It's pretty nice. Yes, exactly. It's the same textbook as linear algebra then, right? All right. Anyways, I wish you guys the best of luck on your final exam, and I'll see you later. Thank you guys for coming. I'll stay here for a bit in case if anyone has any questions.